In this section, we're going to be looking at constructing linear equations that we can use to model real-world behaviors or real-world situations. We'll start off by looking at variation problems, so essentially word problems, where we have to translate statements in plain English into mathematical equations. And then we'll move on to looking at constructing linear models given data. In terms of variation problems, there are two types that we're going to consider. The first will be direct variation problems. Anytime we have a direct variation problem, we're going to look at setting up an equation of the form y equals k times x, where k is some constant that we'll need to solve for in order to produce that equation that we're after. In example 1, we're told that the monthly payment, P, on a mortgage varies directly. So that's going to be the key piece of information that we're looking for to let us know we're using this direct variation approach. So it varies directly with the amount borrowed, B. This lets us know that we can set up an equation of the form P equals, so P varies directly with the amount borrowed, B. So we have our price set equal to the amount borrowed, B, times some constant. What we need to do then is pull the rest of the information that we need out of the problem so that we can solve for that constant. In this case, we're told that if the monthly payment on a 30-year mortgage is $6.13 for every $1,000 borrowed, then we want to use that to find our linear equation. So that price P of $6.13 can get substituted in for P. Our value K is still a constant that we're trying to solve for, and the amount borrowed that relates to that price is $1,000. So we can divide by 1,000 to solve for K to get K is equal to 0.00613, which means we can rewrite our original equation as P is equal to 0.00613 times that value B. In the last part, we're asked to then find the monthly payment P when the amount borrowed is $245,000. Now that we have this equation set up, we can substitute values in for either P or for B to then find the value for the remaining variable. In this case, we're given the amount borrowed. So we'll substitute in for B, 245,000. And then multiplying together will give us $1,501.85. So this is telling us that if we borrow $245,000, then our monthly payment will be a little over $1,500. In example 2, we have a physics problem. The distance s that an object falls is directly proportional. So this is another way of indicating that we're dealing with this direct variation situation. So we're told that it's directly proportional to the square of the time t of the fall. So in this case, the fact that we're saying it's proportional to the square of the time t is going to give us a slightly different model. So we'll have s, the distance that it falls, being directly proportional to the square of the time t. Since our independent variable is being squared, this actually isn't a linear model anymore. This is now a non-linear model. But our book mixes these different problems together, and I like to blend this in because it just gives us some practice with paying attention to the words in our story problem to make sure we're focusing on how to make these translations. It doesn't really impact much of our problem-solving approach. We're still given values for s and t so that we can solve for k. In this case, we're told that if an object falls 16 feet, in 1 second, that's the information that we can use to solve for k. So in this case, dividing both sides by 1 squared would just give us k is equal to 16, meaning our nonlinear equation in this case is s equals 16 times t squared. Then we're asked to find how far the object will fall in 5 seconds, meaning we can substitute in t equals 5, to get 400 feet. And then we're also asked how long will it take an object to fall 144 feet. In this case, we can still use this same equation, but what we'll do is substitute in this value of 144 for s, and then solve for t. Dividing both sides by 16 will give us t squared is equal to 9, and then we can take the square root of both sides. Keep in mind, though, that when we do that, we need to introduce this plus or minus notation. So when we take the square root of t squared, we'll end up with t is equal to plus or minus 3, so either positive or negative 3. But in this case, the only answer that makes sense would be a time of t equals 3 seconds, because a time of negative 3 seconds just doesn't really practically make sense. In our last direct variation example, we're told that the revenue varies directly with the number of gallons of gasoline sold. So that'll allow us to set up the equation R equals K times G. When the revenue is $38, the number of gallons of gasoline sold is 10, which will allow us to solve for K and find that that would be 3.8. So in this case, we again have a linear model describing this situation. Then we want to find the revenue R when the number of gallons of gasoline sold is 14.5. So again, we would substitute in that value for G. To get a revenue of $15.10. I'm sorry, $55.10. So in each of these cases, we set up our model, solved for the constant, and then looked at whatever information we were given, either to substitute in for the independent variable or the dependent variable, and then solve for what was left over.